we've seen that you can get the binomial coefficients for something like x plus y to the fourth power. We know n is 4, and so we said 4c0, 4c1, 4c2, 4c3, 4c4. Critical to start with r of NCR equals to 0. And when we did this, we got 1, 4, 6, 4, 1 for each of these, and they became the binomial coefficients. There's a second way to find this same number pattern, 1, 4, 6, 4, 1, that does not use combinations, and that is Pascal's triangle. Now, Pascal's triangle will give us the binomial expansion coefficients. How do we find Pascal's triangle? Start with a 1, and then write 1, 1. If you can do that, then you get Pascal's triangle. 1 plus 1 is 2. I'm adding these together, and notice the outside slanty pattern there is always going to be 1. Now, I'll do 2 plus 1 is 3, and 2 plus 1 is 3, and I'll add 1s on the outside. Now, 3 plus 1 here is 4, and 3 plus 3 is 6, and 3 plus 1 is 4, and I'll add a pair of 1s on the outside. By the way, 1, 4, 6, 4, 1, that was our pattern when n is equal to 4. 4 plus 1 is 5, 10, when I'm adding these together, 10, 5, and I'll put 1s on the outside. Those are the binomial coefficients when n is 5. How about when n is 6? I get 6, 15, 20, 15, 6, and I'll put 1s on the outside. Now, these are the binomial coefficients when I have, say, x plus y to the 0 power. I'm going to get 1. If I put x plus y to the first power, I get x plus y. If I expand x plus y to the squared power, I get 1, 2, 1. That's when we FOIL. How about x plus y to the third power when n is 3? Then I get 1, 3, 3, 1. Notice, n is 3, I get 4 terms. Those are the 4 coefficients. When n is 2, I get 3 terms. When n is 1, I get 2 terms. The coefficients 1, 4, 6, 4, 1, as we just talked about, are x plus y to the fourth power. It gives us our 1, 2, 3, 4, 5 coefficients. Here we have x plus y to the fifth power, 1, 5, 10, 10, 5, 1. And of course, this last one that I've written I can fit here is x plus y to the sixth power. So that will give us our 7 binomial coefficients. The one with the sixth is to the sixth power. The one with the 5 is to the fifth power. The one with the 4 is to the fourth power. The one with the 3 is to the third power. The one with the 2 is to the second power. This is to the first power. And notice, again, we're starting with n of NCR to the 0 power. Here is Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Sorry, this should be 1, 5, 10, 10, 5, 1. 1, 6, 15, 20, 15, 6, 1. Those are for n equals 0 through n equals 6. And when I say n, I'm talking about x plus y, or first term plus second term to the n. That's the n I'm talking about. Well, what's important to see here is that that same Pascal's triangle can be expressed with combinations. Here is the same Pascal's triangle, this time with combinations. 1, 0, C0. 1, 1, 1, C0, 1, C1. 1, 2, 1, 2, C0, 2, C1, 2, C2. 1, 3, 3, 1, 3, C0, 3, C1, 3, C2, C3, C3. 1, 4, 6, 4, 1, 4, C0, 4, C1, 4, C2, 4, C3, 4, C4. 1, 5, 10, 10, 5, 1, 5 C0, 5 C1, 5 C2, 5 C3, 5 C4, 5 C5. 1, 6, 15, 20, 15, 6, 1. That's for when n is equal to 6. Let's take this one here. 6C0, that's the 1, 2, 3, 4, the fifth term. Notice, if I'm looking for the fifth term, if I'm modeling this on NCR, my R will be one less than I thought because I started counting with NCR equals 0. R equals 0, R equals 1, R equals 2, R equals 3, R equals 4 for the fifth term. Well, I know that that is, from my, if I'll use the shortcut, I could say 4 times 3 times 2 times 1, and I get 4 digits on top, 6 times 5 times 4 times 3. Cancel, 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 cancel. 30 divided by 2 is 15. I know the answer is 15 there. That's the 1, 2, 3, 4, fifth term over. If I flip this and I go to the fifth term, a 1, a 2, a 3, a 4, a 5, it is 15. So you can see I'm not lying. They are the same. It's two different ways to express the same information. Pascal's triangles in numbers and Pascal's triangles in combinations. Use the seventh row of Pascal's triangle to find the binomial coefficients. 8C0, 8C1, 8C2, 8C3, 8C4, 8C5, 8C6, 8C7, and 8C8. So, of course, I could use my definition. NCR is equal to n factorial over n minus r factorial times r factorial and figure out each one of these. But I want to work smarter, not harder. Now, instead of that, instead of figuring out what each of these combinations is individually, I simply went to Pascal's triangle because I know that this 8C0 through 8C8 is going to be the row in Pascal's triangle with the 8 in it. So I made out my Pascal's triangle all the way down to this row. And when I had 1 plus 7, I made 8. 7 plus 21 was 28. 21 plus 35 is 56. 35 plus 35 is 70. 35 plus 21 is 56. 21 plus 7 is 28. 7 plus 1 is 8. I put 2 1s at the end. These 9 terms correspond to 8C0, 8C1, 8C2, 8C3, 8C4, 8C5, 8C6, 8C7, 8C8. And I barely had to do any work to do that. Now, again, you can see if I'm looking for the 1, 2, 3, 4, 5, 6th term, the 6th term will be, if I'm thinking about NCR, it will be when R is 1 less than I would think. For the 6th term, R will actually be 5 because we start counting NCR with R0. Just be careful of that.